A single lithium-ion cell can reach 1,000 degrees Celsius in thermal runaway, hot enough to melt the aluminum fuselage around it. And there are thousands of them on the flight you are on right now. Across roughly 100,000 commercial flights a day, that adds up to hundreds of millions of cells in the air every single day. But airlines are not being reckless. So what makes this manageable, and what makes it catastrophic the moment it is not? The answer involves a cathode chemistry that generates its own oxygen. eSIM, fire suppression agent that cannot stop it, regulations written in the wreckage of real crashes, and an industry that decided it could not ban the very thing that threatens it. A standard cylindrical 18650 cell, measuring just 18 millimeters by 65 millimeters and weighing only 46 grams, concentrates roughly 250 watt-hours of energy per kilogram. Its larger sibling, the 21700 format, pushes this limit to 300 watt-hours per kilogram, packing up to 19 watt-hours of stored energy into a single cell. Beside these cylinders, flat pouch cells strip away heavy steel casings entirely, using flexible laminate foils to shave off weight and fit tightly inside laptops. To put this scale in perspective, the battery inside a typical smartphone contains enough electrical potential to run a household LED light bulb for over an hour. Yet it fits comfortably in a shirt pocket. This extreme concentration of power is achieved through high-performance cathode chemistries, specifically lithium cobalt oxide and nickel manganese cobalt. These formulations maximize storage capacity, but they lack the inherent chemical stability of safer alternatives like lithium iron phosphate. The engineering that prevents this packed energy from discharging all at once relies on a microscopic barrier, the separator. This porous polymer membrane, often made of polyethylene or polypropylene, measures only a fraction of the width of a human hair. Its sole purpose is to keep the positive and negative electrodes from touching, while still letting lithium ions pass through to generate current. A microscopic plastic film is the only barrier keeping stable power from becoming an instant short circuit. How does such a delicate boundary withstand the extreme physical environments of modern commercial flight? When the microscopic separator fails, the consequences are immediate and violent. Under abnormal conditions, polyethylene or polypropylene membranes attempt to prevent disaster by melting shut between 130 and 170 degrees Celsius, choking off the flow of ions. But if physical damage or external thermal stress breaches this thin barrier, the positive and negative electrodes touch directly. This creates an internal short circuit, triggering self-heating that the cell can no longer control. At this stage, the cell enters thermal runaway. The internal chemistry decomposes, releasing stored energy not as electricity, but as intense, concentrated heat. Temperatures within the failing cell climb rapidly into the 800 to 1,100 degrees Celsius range. This is nearly 3 times the melting point of lead, which liquefies at 327 degrees Celsius and approaches the temperature of a glass-blowing furnace. The cell becomes its own furnace. This extreme thermal energy does not remain confined. In a typical battery pack, individual cells are packed tightly together, often separated by less than a centimeter of space. The outer casing of the failing cell becomes a thermal bridge, radiating heat directly into its neighbors. As these adjacent cells are heated past their own shutdown thresholds, they too break down, adding their own stored energy to the fire. A single cell failure quickly propagates across the entire pack. One failing cell initiates a domino effect. If heat were the only challenge to manage, simply smothering the source might suffice. But thermal energy is only the first half of the equation. Why does a traditional fire extinguishing agent fail to halt this chemical chain reaction? Unlike a typical fire that relies on oxygen from the surrounding air, a decomposing lithium-ion cell provides its own fuel and oxidizer. When layered oxide cathodes like lithium cobalt oxide or nickel manganese cobalt break down under extreme heat, they release lattice oxygen directly into the cell's interior. This liberated oxygen mixes with volatile, vaporized organic electrolytes, venting a highly combustible gas cloud of hydrogen, carbon monoxide, and light hydrocarbons like methane. This chemical cocktail behaves less like a burning piece of paper and more like a localized gas generator. This is where aviation's primary line of defense fails. Since the 1970s, commercial aircraft cargo bays have relied on halon 1301 to extinguish fires. Halon works by chemically interrupting the combustion chain in the surrounding air. However, it cannot penetrate the sealed steel or laminate casing of a battery cell, nor can it halt the internal self-sustaining chemical decomposition occurring inside. Federal Aviation Administration testing confirmed this limitation. While a 5% concentration of halon can knock down external flames, it does not stop the runaway cell from venting hot gases, nor does it prevent the cell from reigniting once the agent dissipates. Aircraft fire suppression systems were designed for Class A and Class C fires, smoldering baggage, paper, or electrical wiring. They were never engineered to fight a chemical reaction that feeds itself from within. The system is mismatched against the chemistry. How does an industry manage a hazard that its standard defenses cannot extinguish? At 38,000 feet, there is no shoulder to pull onto. If a runaway reaction begins in flight, the aircraft itself becomes a pressurized containment vessel. Cargo compartments are densely packed, shared environments where consumer goods, personal mail, and shipping pallets sit tightly side by side. Within these holds, a single thermal event does not remain isolated. It quickly becomes a systemic threat as intense heat radiates directly into neighboring baggage, turning adjacent cargo into fuel. This hazard is compounded when shippers misdeclare or mislabel cargo, concealing high-energy lithium batteries inside standard freight and leaving flight crews completely unaware of the volatile materials beneath their feet. To govern this invisible risk, the aviation industry utilizes a highly structured operational language of containment, codified under the International Civil Aviation Organization Technical Instructions and the International Air Transport Association Dangerous Goods Regulations. These frameworks establish clear, non-negotiable operational boundaries. For example, spare lithium-ion batteries, with their exposed and vulnerable terminals, are strictly prohibited in checked baggage and must remain in the passenger cabin where crews can intervene. Conversely, batteries installed inside equipment are permitted in the hold because the surrounding device chassis provides an initial layer of physical protection. For everyday travelers, safety is managed through precise energy thresholds. Batteries rated up to 100 watt-hours, which cover standard smartphones, tablets, and laptops, are permitted in carry-on luggage. High-capacity devices rated between 100 and 160 watt-hours require explicit airline approval, while anything exceeding 160 watt-hours is banned from passenger transport entirely. Beneath these consumer limits lies a global engineering gatekeeper, the UN 38.3 testing standard. Before any battery design can be certified for air transport, it must survive 8 separate environmental trials, including altitude simulation, extreme thermal cycling, vibration, and impact testing. The entire global supply chain hinges on this rigorous testing gate. Yet, despite these preventive measures, the real-world performance of these defenses remains bound to human compliance and mechanical integrity. How did the aviation industry react when these regulatory and physical barriers faced their ultimate catastrophic failure in the open sky? A complete ban on carrying lithium batteries by air would immediately stall the global economy. Modern supply chains, from urgent medical shipments like cardiac pacemakers to the rapid delivery of consumer smartphones, rely on air freight. In 2022, e-commerce represented nearly $1 trillion in global trade, with millions of battery-powered devices moving through cargo networks daily. Grounding these products would disrupt international commerce in a way that physical containment measures do not. This reality forces a pragmatic calculation. Airlines and regulators are not ignoring the hazard, they are accepting managed exposure. Stopping the entire aviation system to achieve absolute safety carries an unsupportable economic cost. Instead, the industry invests in physical containment, state-of-charge limits, and specialized cabin packaging. The cost of these safety barriers represents a tiny fraction of operating budgets, while a total ban would shutter entire industries. Regulators choose a workable reduction of risk over unachievable chemical purity. How does an industry build an effective fortress around a chemical hazard that cannot be completely banned? As the energy density of commercial cells rose toward 250 watt-hours per kilogram, packing more power into lightweight devices than ever before, the theoretical risk of thermal runaway became a real-world crisis. On September 3, 2010, UPS Airlines Flight 6, a Boeing 747-400 freighter, departed Dubai. Within 21 minutes of takeoff, a fire broke out in a cargo deck containing thousands of lithium batteries. The intense thermal energy quickly overwhelmed the cargo hold's Halon 1301 suppression system, destroying flight controls and leading to a fatal crash. The accident proved that bulk lithium-ion cargo could generate self-sustaining fires that outran existing aviation safety systems, forcing regulators to reconsider cargo hold vulnerabilities. Less than 3 years later, the risk migrated from cargo compartments directly into aircraft systems. In January 2013, an auxiliary power unit lithium-ion battery caught fire on a Japan Airlines Boeing 787 parked in Boston. Days later, a second battery fault forced an emergency landing of an All Nippon Airways 787 in Japan. In response, the Federal Aviation Administration issued an emergency airworthiness directive, grounding the entire global 787 fleet, the first such action since 1979. This grounding forced Boeing to completely redesign the battery housing, wrapping the cells in heavy-gauge stainless steel containment cases, essentially transforming the battery compartment into a miniature bank vault designed to vent hazardous gases directly outside the airframe. The mounting evidence of cargo and systems vulnerability led to unprecedented regulatory intervention. On April 1, 2016, the International Civil Aviation Organization enacted a global ban prohibiting standalone lithium-ion batteries from being carried as cargo on passenger flights. Under this new mandate, bulk shipments were restricted entirely to cargo-only aircraft, and their state of charge was strictly capped at 30% to minimize the energy available to feed a thermal event. Just months later, the threat entered the passenger cabin. In October 2016, following dozens of spontaneous fires, the United States Department of Transportation issued an emergency order banning the Samsung Galaxy Note 7 from all flights. This ban proved that consumer electronics, normally as harmless as a book in a seatback pocket, could threaten an aircraft overnight, forcing airlines to implement strict cabin safety protocols. Every failure pushed the system to adapt, turning hard lessons into tighter containment boundaries. How does the modern aviation system construct physical and chemical barriers to neutralize this volatile chemistry in flight? In the cabin, the primary defense against a runaway consumer device is the containment bag. Constructed from advanced materials that withstand temperatures up to 1,200 degrees Celsius, these bags allow flight crews to isolate a smoking smartphone or tablet before the fire spreads. Within 30 seconds, the bag's internal layers quench venting gases and contain the thermal event. But a solution engineered for a single device cannot protect an aircraft from systemic failures. For onboard systems, the defense is integrated directly into the airframe. Following the 2013 grounding, the redesigned Boeing 787 auxiliary power unit battery was encased in a 2.5 millimeter thick stainless steel enclosure. This heavy gauge housing acts as a miniature vault. If a cell fails, the box contains the pressure and routes flammable gases directly overboard through a dedicated vent tube at 12 pounds per square inch, isolating the reaction from critical avionics. The battery becomes its own containment zone. Deep in the cargo holds, where physical intervention is impossible, protection relies on structural barriers. Modern cargo compartments are lined with fire-resistant materials, such as 3M Nextel ceramic fabrics, designed to maintain compartment integrity for at least 30 minutes. This containment window buys precious time for the aircraft to divert. Ultimately, the most effective defense is operational control before takeoff. By enforcing a strict 30% state of charge limit on bulk shipments, regulators reduce the chemical energy available to feed a fire. At 30% charge, cells lack the energy density required to sustain flaming combustion. Lower energy means lower risk. But what happens when these rigid regulatory boundaries are tested by the realities of global shipping? Subscribe for more deep dives into the engineering that keeps our skies safe. Every protective barrier relies entirely on human compliance before the aircraft leaves the ground. Yet the human element remains the most difficult variable to control. In global logistics, some commercial shippers intentionally misdeclare cargo, labeling high-density lithium shipments as household goods or plastic toys, to bypass expensive, dangerous goods fees and tedious certification paperwork. At the passenger terminal, the breakdown is born of simple ignorance. Travelers routinely pack high-capacity power banks and spare lithium-ion batteries into checked luggage, unaware that these portable energy reserves are tightly regulated hazards. The Federal Aviation Administration recorded 55 lithium battery incidents over a recent 2-year span, showing how frequently these hazards slip past security checkpoints. This leaves flight crews in an unforgiving position. At 30,000 feet inside a sealed aluminum fuselage, pilots and cabin attendants must fight volatile chemical fires caused by a stranger they will never meet. It is a direct conflict between the demands of global commerce and the uncompromising laws of aerodynamics. While international regulators issue steep fines and mandate strict testing standards, they cannot physically govern every individual decision at the cargo dock or the boarding gate. Can any screening system realistically catch every violation before departure? When you power down your phone for takeoff, you hold aviation's most complex compromise. Absolute safety dictates banning lithium. Global commerce demands carrying it. This leaves flight physics and volatile chemistry in a permanently engineered truce. Every journey relies not on a risk eliminated, but on a hazard meticulously contained. Subscribe for more deep dives into the hidden engineering of modern transit.